It's time for our third talk. It's from Fred Watson on how Australian astronomers cooked up a high fibre diet. And as you can guess, it's not about food. Fred is one of the few people who needs no introduction, but I will just say that he spent 20 years as astronomer in charge of the Anglo-Australian Observatory. More recently, he was astronomer at large for the Australian government. He's still at large, having been last heard of in Cyprus, from which where he kindly recorded his talk, and he gives apologies for not being able to be present in person.
Hello everybody, my name's Fred Watson. I am an astronomer. Until recently I was the Australian government's astronomer at large. I'm now Macquarie University's astronomer on the loose. I'd like to begin by thanking the organisers for inviting me to give this presentation, and I'd like to apologise as well that I can't be there in person. I would love to have been at this meeting. I'm afraid there was no way that I could manage it. So you've got to put up with the avatar at the moment. What I want to talk about is the technique, the astronomical technique of multi-fibre spectroscopy, which is a very simple idea that takes the light from individual objects in the field of view of a telescope, aligns an optical fibre with that image, and then rearranges all those fibres along the slit of a spectrograph equipped with a two-dimensional detector. And while it might not give us the answer to life, the universe and everything, it is certainly a very productive technique in terms of astronomical surveys. There are challenges. The two most important ones are, first of all, the fibres need to be aligned with your target with an accuracy in the region of 1/100 of a millimetre, 10 microns. And the other is that the fibres need to be of a special kind that will preserve the profile of the beam of light that the telescope is delivering. So it was not an invention of Australian astronomers. The idea for this technique came in the wake of the first commercially available low-loss fibres. That occurred in 1970, but it was Roger Angell of the University of Arizona who first proposed the idea of using fibre optics in this way. And a few years later, he and one of his research students, John Hill, built a prototype to demonstrate that this actually was feasible. And then very shortly after that, the idea was picked up by two scientists closely involved with the Anglo-Australian Telescope, Dave Carter, who was then working at the Anglo-Australian Observatory as it then was, and Richard Ellis of the University of Durham. They put a memorandum out in 1981 suggesting that this technique be used at the AAT. So there was a very small group internationally of people who took this idea and attempted to turn it into reality. This is a picture taken at one of the conferences in Tucson in the early 1980s with some of the early proponents of the technology. Ralph Powell, who I later worked with at the Royal Greenwich Observatory, Peter Gray, who took up the idea at the Anglo-Australian Telescope, and I'll tell you more about his work in a minute, Sam Barden, who later became the AAO's instrument manager, Ian Parry of Durham, interested in robotics applied to this technology. John Hill, the first PhD in multi-fibre spectroscopy in the world, and Fred Watson, who was the second. I worked then for the Royal Observatory in Edinburgh, but I was stationed at the United Kingdom Schmidt Telescope. And there were colleagues at ESO also working on this technology. So Peter Gray took the idea and turned it into reality by drilling accurately positioned holes in a metal plate, putting them at the focus of the Anglo-Australian Telescope, the Cassegrain auxiliary focus, and then feeding them to an existing spectrograph, the RGO spectrograph. It had 25 fibres within that 12 arc-minute field, commissioned for Galaxy work in 1981. Ellis et al. Were the first users, but you might notice that scribble on this field plate there, Watson 1983. I think I was the first person to apply this technique anywhere in the world to stars rather than galaxies. Peter then took things a step further by increasing the field of view of the Anglo-Australian Telescope's FOCAP system, which was just an acronym for fibre optically coupled aperture plate. 64 fibres in the full 40 arc minute field at Cassegrain focus, and that became very, very successful. So in a sense, Peter turned the technique from an interesting idea, came from Arizona, into something really useful for astronomical observations. And as I said there, by 1987 it was using 30% of all the time on the telescope. Experiments at the University of Durham to roboticize this eventually led to the idea of 2DF, the 2-degree field system on the AAT. And that had its origins with work by Keith Taylor and Peter Gray, a design study in September 89. You can read all the aspects of it there. 2DF is so well known that it's almost superfluous to put these details in. But that was the thing that eventually came into being, of course, on its own top-end ring, at the top of the Anglo-Australian Telescope. This lovely view showing the robotic fibre positioner on the field plate nearest to the camera. There are two field plates. One of them is looking at the mirror, so that's the active one, which is taking light from the sky, and the other one has the robotic fibre positioner moving 400 fibres around, each one equipped with a magnetic button on the end that sticks it to a steel plate, and with a prism to bend the light from the telescope mirror into the fibre, and then they retracted automatically, so the robot could move them around with impunity, and it turned out to be, as you know, extremely successful. The opening ceremony was less successful. Some of you who were there might remember the weather was absolutely foul. I think half the guests didn't make it just because their aircraft had to turn back. Things were so bad at Coonabarabran Airport. Took another 6 months or so to get useful spectra from the instrument, and it was sort of in production by the middle of 1997 when it started work on perhaps its masterpiece, that earliest demonstration of the potential of the multi-fibre technique, the 2DF Galaxy Redshift Survey, which I don't really have time to talk about in detail, but is very well known, a milestone perhaps in the science of astronomy, with that sort of honeycomb structure of the universe being so well revealed there. I've noted a few other people who were very instrumental in making that survey work. Russell Cannon was director of the AO at the time, Matthew Collis, one of the PIs, Ian Lewis, who actually turned 2DF from something that was a very cantankerous instrument into quite a reliable operation. Carl Glazebrook spent, I think, a year, if I remember rightly, at Siding Spring, really knuckling down onto the software aspects of what we needed for the survey. And in a sense, the rest is history. 2DF is still a workhorse instrument on the telescope. The spectrographs have gone through a number of iterations. AA Omega replaced the two telescopes mounted, spectrographs mounted on the top end ring. Hermes, that great high-resolution spectrograph for the galactic archaeology work in the project which is known as Galar. Koala and Hector both integral field unit spectrographs, so you're there not just looking at multi-objects via optical fibres, but actually dissecting galaxies into their individual pixels, if you like, and taking a fibre on each. Hector, which is the current one of the current main instruments on the Anglo-Australian Telescope, commissioned about a year ago. Here is its PI, Julia Bryant, with the Hector field plate. Moving on, though, from the Anglo-Australian Telescope, something that I was perhaps more closely involved with was the work at the United Kingdom Schmidt Telescope. I was at that time, in the early 1980s, on secondment from the Royal Observatory, Edinburgh. And it was in thinking about what Peter Gray had done on the Anglo-Australian Telescope that led the then astronomer in charge of the UK Schmidt Telescope, John Daw, who we sadly lost to pancreatic cancer in 2004. He was a commissioning astronomer on the AAT, but he was the astronomer in charge when I started my time at the Schmidt Telescope in 1982. And we got our heads together and realised that there might be advantages in putting multiple fibres on to the Schmidt. And in fact, we produced this little paper in July 1982, a proposal for a radical extension in the use of the UK Schmidt Telescope to the management of the Royal Observatory in Edinburgh. And the bottom line here with this paper was simply that the information throughput of the Schmidt is comparable with that of the Anglo-Australian Telescope in terms of the what's called the omega product, the étendue. They are equal, actually, with the AAT with a 2-degree field, as it then didn't have, but was going to have, and the UK Schmidt Telescope with its 6-degree field. The problem was the Schmidt Telescope at that time was sort of on an industrial scale, surveying the southern sky with the photographic sky survey. And that meant that anything that we did, and this was mandated by the Astronomer Royal for Scotland, Malcolm Longair then, who was actually my PhD supervisor, along with Russell Cannon and Don Morton, that it was mandated that the work of the photographic survey should not be interrupted by our experiments with fibre optics. So it meant that the region where the photographic plates were held, the focal surface of the telescope, had to be accessed by fibres in a way that was compatible with photography. And that meant building things like this, which was a field plate designed to take fibres and rather than photographic plates. The issue being that the focal surface was curved, and so the field plates themselves had to be curved. And what we developed, and this was a suggestion due to David Malin, the idea was to use the photographic plates taken by the Schmidt, put them, process them as positives on a 1 millimetre thick glass plate, so that the star images themselves were transparent, and then we could optically align each fibre with one of those images, stars, galaxies, whatever, and cement it there with UV curing cement. All ideas from David Malin's fertile brain, and that's what we did. We sometimes ran into troubles. Not every plate behaved the way you wanted it to, especially after you'd spent time fibering it up. But we evolved this mandrel, the thing that bent the field plates, on a hexagonal base to allow us access to the back of the field plate to stick the fibres on, as you can see here, but still preserved the fidelity of the surface so that the field plate didn't break. And that's a fibred up field plate with the system that we called flare. I'll tell you what that means in a minute, but let me also point out the spectrograph that we used was the most rudimentary kind. It used a Pentax film camera. We hypersensitized the film and actually managed to get some useful spectra out of it, digitized on a PDS machine. That was the optical table, the optical bench for the spectrograph, which cost a lot more than the spectrograph did. That was the first one that we built. So FLARE was the fibre-linked array image reformator. It demonstrated that the Schmidt was a worthwhile instrument for developing this technology, and we moved on to a sort of prismatic system, still cementing fibres onto glass plates, but using a right-angle prism as well, panoramic area coverage with higher efficiency to give us the whole field of view of the telescope rather than hexagonal holes. That was panache. And that let us play around quite a lot. This was experiments. We then had a CCD camera built by Paddy Oates of the University of Durham, and it let us try out, for example, using multiple spectrographs rather than just single ones. Here's a photograph taken during that period when panache was on the telescope. We then postulated a further version, which I wanted to call finesse, but it was Duncan Waldron, now in Brisbane, who remarked that this probably would stand for fails to interest nearly everyone save spectrograph engineers. So in the end we called it Flare 2, 90 fibres. I was the instrument scientist along with Quentin Parker, who then took over when I left the Schmidt to return to the Royal Observatory in Edinburgh in 1992. Peter Gray developed a spectrograph, an all-Schmidt spectrograph, fibre Schmidt, which is why it was called FISH, and Tim Bedding built something called AutoFred, which was designed to automate what I was doing in the manual setup of fibres. And in a sense, all that then led the way to the 60F system, a fully engineered system, which is what really put fibres very much on the map on the Schmidt telescope. Approved by the Anglo-Australian Telescope Board in 1998 and built in a remarkably short period, actually, of 3 years. I was project scientist for the instrument, but the commissioning scientists who really did the nitty-gritty as the instrument was commissioned on the telescope were Will Saunders and Quentin Parker, seen here with the 60F robot, because it had a fibre positioning system very similar to that of 2DF, except the field plates were interchangeable within the Schmidt telescope. It was still doing photography at that time, and so the field plates for 60F had to look like photographic plates to the telescope, but they were set up on a robot, and it was done. I didn't mention the sort of buffered system. I mentioned it for 2DF. We had the same thing on 60F. You had one field plate in the telescope actually doing the observing, while the other one was in a separate robot room in the dome. Will Saunders, of course, perhaps better known generally for his artistic work on the Sydney Opera House in 2003. But that's a picture of the Schmidt telescope. The sort of wooden building there on the left is where the robot was housed. To the right, underneath the icon that's got my face on it at the moment, so you can't see it, there was a room for the spectrograph, which was an evolution of Peter Gray's fibre Schmidt spectrograph. What did the system do? Well, the science was, I think, groundbreaking in its time. 2 projects. The one that it was really commissioned for was the 60F Galaxy Survey. So this was something similar to the 2DF Galaxy Redshift Survey, except we also included peculiar velocities for a subset of the galaxies, 150,000 galaxies, but it was the whole southern hemisphere, whereas, of course, the 2DF Galaxy Survey was slices through the southern hemisphere. Matthew Collis, the PI, and some very important proponents who really sold the idea to the Anglo-Australian Telescope Board, which is why it happened in the first place. I might mention that the cost of 60F was about $1 million by the end of it, but that's only a tenth of what 2DF cost on the AAT. And then when the 60F Galaxy Survey was nearing completion, we looked at an alternative. We had a higher dispersion option in the spectrograph. We were using by then volume phase holographic gratings, and we did what was called RAVE, the Radial Velocity Experiment, the radial velocities and physical parameters of 500,000 stars, a 9-nation collaboration led by Matthias Steinmetz at the Astrophysical Institute of Potsdam. Great science. This is some spectra from RAVE. We were looking at the calcium triplet region in the near infrared, and you can see just by looking at that how the radial velocities of those stars are changing by the wiggly lines that you can see. Spectra for each of the 150 target objects that we could look at, and the RAVE survey, by the time we'd finished in 2013, just about the time that the observatory almost disappeared because of the Wombalong fire. The RAVE actually finished just after the Wombalong fire. I took the last observations in April 2013, but that's the set of 500,000 stars on a projection of the celestial sphere, and you can see there the change in colour, which represents, of course, the solar motion. It's the reflex solar motion that you're looking at there. 60F was, for all it was a robotic instrument, it was very labour intensive, and so huge kudos must go to the observers, many of whom are shown here on the occasion of the 30th anniversary of the Schmidt Telescope in 2003, but many others whose pictures aren't on there, who made those two 60F surveys successful. It was hard work, and many of us still remember it. I still have it in my dreams. I can't believe it all those years later, 12 years after we completed the survey. What's happening at the Schmidt now? Well, the next step was something that really John Doe and I were thinking of back in 1982, the idea of fibres equipped with micro-robots so that they could wander around on the focal surface so that you could position them all simultaneously. There wasn't a time lag while a pick-place system moved the fibres around. And we not we, because I was not involved with this, I was just cheering them on from the sidelines. At the AAO, they perfected starbugs and built an instrument called TAIPAN, which had, again, about 150 fibres, each individually addressable with a microprocessor. Sadly, TAIPAN took so long to perfect that the surveys that we had in mind for it, one called FunnelWeb and one called TAIPAN, were really superfluous by then. And so that's the situation at the Schmidt now. The telescope is still available with TAIPAN on board, but it's sort of mothballed because there isn't a competitive piece of work for it to do. And I might mention too, before I wrap up, one of the things that has made AAO and Australian astronomy generally, because the University of Sydney, Macquarie University, ANU are also involved with this technology, is exporting it to other observatories. AusPos for the VLT back in the early 2000s. The 60F was a prototype for AusPos, and here is Foremost, which is, as we speak, being commissioned on the Vista telescope at Cerro Paranal, 2,400 fibres, which can be reconfigured to any given field within about a minute. It is extraordinary, that technology. Finally, one of the spin-offs, I guess, with the AAO's work on fibres was to think about what you might do with light once you've got it into a waveguide, an optical fibre. And my contribution to this, if I can put it that way, was a paper back in 1995, some people call it the beginning of astrophotonics, where I proposed a design for a spectrograph which was about the size of a deck of cards, multi-objects fed by fibres, but the light manipulated by waveguides once you've got it into the device. And that's sort of now turned into the whole science of astrophotonics, with basically photons being manipulated like electrons in waveguides, as well as techniques like the OH line suppression, which was perfected perhaps 20 years ago now. This is Joss Bland Hawthorne's brainchild with other people involved, but an extraordinary way of dealing with the forest of OH lines particularly in the H band of the infrared spectrum. So squeezing light into fibres leads you down all kinds of very, very productive paths, and I think we're really only seeing the start of the amazing benefits that astrophotonics can bring us in the science of astronomy. So that, everyone, thank you for your attention. That is how Australia's optical astronomers cooked up their high fibre diet, and thank you very much for watching.